really. And thank you to the organizers for having me. Also, this is my first time being in South India. I've never been here. From what I can tell from watching movies, this is a very beautiful place. So thanks for giving me an opportunity to be here. Okay, so this talk will be about TASEP, which we saw in the morning. But even before I talk about TASEP, I would like to explain the motivation for studying this problem of shocks in TASEP. So it has to do with studying waves, the motion of waves. So, so how do you describe the motion of a wave, right? So if you have a wave, okay, so wave is a three-dimensional object. So if you take a one-dimensional cross-section, then what you will get is some wave profile, which is a shape indexed by x, which is a real number, and it moves in time. So there is time, and there's a function u of t and x that will describe the shape. Okay? The wave equation is the prototypic model for understanding the motion of a wave, right? So the wave equation will say that if you have a function u, just like that, of one space and one time dimension, then this E describes the motion of the wave in time as it moves through space, right? So this is the second order PDE. There are two time derivatives and two x derivatives. An even simpler version of the wave equation, a first order PDE, is just when you remove one time derivative and one x derivative from this, and you write this down, right? So why do I call this also a wave equation? Well, let's see what happens. So if you take this equation and you solve it, you are going to get a solution that looks like the following. So you take the initial condition, let's call that f, and then utx is just f evaluated at t plus x. Okay? What that means is if you start with f, which is the shape at time 0, and then you see what the wave does at further times, it just moves at constant speed in some direction. Right? So this is the motion of a wave. Okay? So this is the simple version of the wave equation. The more complicated version, the actual wave equation, is just the superposition of two traveling waves that look like this, where f and g are going to come from the initial condition. So because this is the second order equation, the actual wave equation, there are going to be two initial conditions, and each will determine the f and the g. Okay? So you have a simple wave equation, you have the actual wave equation, and what they do is they have solutions that just move at constant speed while keeping their shape. But if you're familiar with wave motion, you know that waves can very easily do something like this, right? So if you're standing at the beach and you're watching the wave come into you, you will see that it starts out with a very nice shape, but as it comes closer and closer to you, it sort of curls into itself until there's a point where it stops being the graph of a function. Okay? And that's called the shock in the wave. Okay? So the goal is to sort of understand certain stochastic analogs of this kind of shocks and try to understand what happens, just at the formation of the shock. Okay? So to understand this, let me just first say the following. So how would you model the formation of a shock? Or rather, how would you actually even model a shock? Okay? So it's very hard, because once the shock is there, u is not a function anymore. This is not a graph of a function. So you cannot write down some equation to describe it if it's not a function anymore, at least not in the classical way. Okay? What you can do is describe the wave just as the shock forms. So it makes sense here, it makes sense here, and it will make sense until some point here, just until the shock forms. And once the shock forms, then the equation will cease to make sense. And the way this is done is you take the wave equation and you add to it nonlinear terms. Okay? And whenever you add these nonlinear terms, you will see phenomena like this. Okay? So our prototype for this is this Burger's equation, which takes the simple wave equation with one x derivative and one t derivative and adds to it this kind of nonlinear term and gets this equation. And it has the property that if you start with even a smooth wave profile, okay, so long as the wave decreases somewhere in the direction of flow, so here it decreases in the direction of flow, then in finite time it's going to create a shock. Okay? As long as, so this is one of the main properties of the Burger's equation. So if you want to understand sort of stochastic analogs of wave motion and shock formation, you would like to start with this Burger's equation and find some stochastic way of modeling this equation. Okay? So that's going to be the first part of this talk. Is that clear? Okay. Okay. So how do you come up with a stochastic model of Burger's equation? You do so by using interacting particle systems. Okay? So there are many interacting particle systems that actually model Burger's equation. There is even a theory for this. But one of the most basic is the TASEP, which we saw during the talk in the morning. Okay? So the TASEP stands for Totally Asymmetric Simple Exclusion Process. And I'll explain, just for the sake of this talk, what it is that it does. So it's a particle system on the integers. So you have the integers, and at time 0, so it's a particle system, so it's gonna change with time. So at time 0, you put particles on the integers any way you want. Okay, so here I have a particle here, here, no particle, no particle, no particle, particle, no particle, particle, and so on. And this goes on infinitely on all the integers. And then every particle wants to jump to the right, and only to the right. Okay? And every particle will jump at rate 1. So it moves in continuous time, and it just wants to jump at rate 1. And everything wants to move independently of the other. So what this particle does doesn't have anything to do with what this particle does, doesn't have anything to do with what this particle does, and so on. Except there's a very important rule, the exclusion rule, which states that no particle can jump on top of another particle. Okay? So for example, if I'm here at -3, there's a particle. If it wants to jump now, it's not allowed to do so because there's a particle at -2. But if the particle at -2 moves 1 unit to the right, then the one at -3 is allowed to move. Right? So subject to this exclusion rule, the particle just moved to the right independently at rate 1. So that's the TASEP. Okay, so I say that this TASEP is a stochastic description of Burger's equation, and the way it works is the following. So you go into the TASEP, right here, and at time 0, you are allowed to put particles any way you want. Okay, so you just put the particles any way you want. Okay, but now you need to make sure that the following happens. You need to make sure that there is some macroscopic density in the way you have placed the particles. That means that if you take a very large interval, say from AL to BL, where L is a parameter, okay, at time 0, and you look at the number of particles in that interval, and you divide by L, so you look at some kind of density, okay, and you take a limit as L goes to infinity, okay, so this limit should exist for every choice of interval AB, and moreover, this should be represented as the integral from A to B of some density, U0, okay? So that's going to be your initial data for Burger's equation. So you have to make sure this happens. And once this happens, there's a theorem that says that for farther times, there's going to be a macroscopic density in the sense that, again, if you look at the number of particles in a very large interval from AL to BL at time, which is macroscopic, so T times L. T is the parameter. So you look at the number of particles and you divide by L to get a density, and then you take a limit. And you notice that this limit, this is a random number because this is TASEP at some macroscopic time, so there's some dynamics there. So the theorem is, so one part of the statement of the theorem is that this random number is in fact deterministic, and not only that, but also that it can be represented as integration against a density function ut of x. Okay? So for every fixed t, this is a density in the x variable. Okay, so this kind of object is always a measure. Just because of the way I've defined it, it's always a measure. The point is this has a density now. And this density, it solves Berger's equation in this form. Okay, so it's not the classical form, but in this form, it solves Berger's equation with the initial data that you put into this. Actually, if you look at this equation, you notice that your U0 may not even be a continuously differentiable function. So when you want to talk about solutions of this, you have to talk about them in the weak sense. If you talk about them in the weak sense, there can be more than one. So you have to pick out the right one. And the right one is something called the entropic solution. And this TASEP actually picks out the entropic solution, actually gives you the solution which is the physically relevant solution. And this is part of some rather general theorems about interacting particles. I will not describe that. What I would like to describe is how we specialize this to a certain initial condition, which is the problem of the shock that I want to study. Okay. Okay. So here's the initial condition that I want to study. Okay, it's the step initial condition. So you want to study shock. Okay, so now I consider an initial condition where you have two densities, rho minus and rho plus. Okay, and U0 is just rho minus to the left of 0 and rho plus to the right of 0. Okay, so it's just a step function, and rho minus is less than rho plus. Okay, so to create a shock, you need to have rho minus less than rho plus. If you recall, I said the Berger's equation will run into a shock if the initial density decreases in the direction of flow. But here, I have this density which is increasing in this will be the direction of flow, so it is increasing. So why is it that I need it to be increasing? The reason is because my Berger's equation is in this form and not the standard form. So in this form, to create a shock, you need the density to increase in the direction of flow, and I just look at the most basic case of the shock, which is the step function. So now if you solve this equation, the entropic solution is just a traveling wave. So the wave keeps its shape and just moves at constant speed. The speed is this number nu, which is 1 minus the sum of the two densities. So that's the speed at which this just moves in this direction, or it could be in this direction. And this is the shock in TASEP. Okay, so this jump in the density is the shock in the TASEP. I already started with a shock. That's right. I'm already starting with a shock. That's right. So if you want to understand in terms of the TASEP, you just have to realize that the particles which are to the left of 0, because they have density rho minus, they're going to move at speed 1 minus rho minus. Whereas these guys to the right of 0, they're going to move at speed 1 minus rho plus. Okay? And 1 minus rho minus is bigger than 1 minus rho plus. So there's going to be a traffic jam, and that traffic jam is the shock. And that just moves through the system at speed nu. Okay? So that's all that's going on here. Okay, so suppose I model this initial step function, which is the shock 1. Okay, so and suppose I do it in a deterministic way. This is actually going to be crucial. So there are many ways to model this density because it's macroscopic. You can make macroscopic changes and it will never show up. But you're not allowed to add randomness to your initial data. You have to do it in a deterministic way. Okay? So if you do that and you observe the TASEP, you will see some macroscopic density that just moves in time in this direction. And then you imagine that there's some kind of macroscopic density of the particles, which is in the green here. Okay? And in the TASEP, this macroscopic density, it's not, macroscopically the shock is not abrupt. There is some window which is of macroscopic width where it goes from rho minus to rho plus. And what we would like to do is zoom into this shock window and observe this sort of green curve here, sort of the TASEP system within here, and understand the particle fluctuations there. That's going to be sort of the process at the shock. I'm going to get, so at this point I haven't explained the size of the window and what's the order of the fluctuation, so I'll explain all of that. Yeah. But yes, but you imagine there's some window you'd like to zoom into there and understand. Right, right. So this, so I imagine this is macroscopic time here, right? So it says t is very, very large here, right? Okay, all right. So I will do this in a very mysterious way. Won't explain right now why, but the way I will do this is by rescaling the two density parameters, rho plus and rho minus, in a very particular way, which is the following. So I'm going to soften the shock, okay? So this is how I do it. So I will write rho plus minus as 1. Okay, so it's some perturbation around 1/2. So it's 1 plus minus some parameter beta, which I introduce, beta times t to the minus 1/3, where t is also some parameter, but this parameter is TASEP time. Okay, so you take large TASEP time, you introduce some beta, and you write rho plus minus in this form. So now the difference between rho plus and rho minus is about beta t to the minus 1/3. It's very small if t is large. Okay? And then you will run the TASEP to time t, where t is this parameter here. Okay? And then after having run this to time t, you're going to zoom into that shock window. And you're going to observe fluctuations of the shock as t goes to infinity, keeping beta fixed. And then you will let beta go to plus infinity. Yeah? Right. So when you do this kind of limit, when you do this kind of degeneration, you get more structure, at least in the correlation functions. So this is where integrability comes in, and this is a conference on integrability. So that's right. Not intermediate disorder. It's sort of like you will see. So this kind of scaling, essentially what it means is, basically it just means that you can take a large time. So the issue here is, if you try to understand this for large times, of course you can write formulas, but those formulas are not, you get determinantal formulas where the kernels are not well behaved for large times. Whereas if you do this scaling, you will get a determinantal formula where the kernel behaves well in large time. In the large time limit, you will get Fredholm determinants, which are easier to analyze in this beta as opposed to just doing it at first. It's not quite intermediate disorder. It's more like sort of a type of KPZ scaling. The initial data is set up to be on the KPZ scale. So you'll see. I'll explain that. Okay, so the idea is to understand this double limit of t and beta and then recover the macroscopic shock. I have not explained why I have scaled it. Those were actually the questions. And so I'll say, this is sort of a judicious choice of scaling, and it's motivated by some kind of KPZ theory. Okay, so what are we going to be able to do? What we're going to be able to do is, so what we would like to be able to do is take this process that looks like this, and there's some shock, and we want to zoom into this window, and we would like to write down formulas for the distribution of particle positions within this window. Okay? So having written down those formulas, we would like to take a large time limit to get the distribution, the large time distribution of what happens in this window with the beta being fixed. And that's something that you can do if you rescale your parameters like that. And having done so, what you will find is that we get Fredholm determinants that describe the distribution functions, which then you can analyze in this large beta limit to get basically the description of the shock process at the level of the process. Okay. Okay, so this is how we'll do it. So you take the TASEP, and you will tag the particles in the following way. So here's the TASEP, and here are the particles, and you tag them. So the first particle to the left of 0 gets number 1, and then the one to the left of that is number 2, number 3, and so on. And then it goes 0, minus 1, minus 2, and so on. Is that clear how I tag the particles? Okay. And main thing, the main observables here is going to be the position of the tagged particle. So x tn is position of particle number n at time t. All right. So these are the main things that we want to compute distributions of. And now you need to do a little calculation to see where the shock is macroscopically. Okay, so we know that the shock is at position nu t. So macroscopically, the particle that hangs around this position nu t is going to have a number which is the product of the two densities times t. Okay, so if you follow that particle up to time t, it's going to be macroscopically in this location, and I give it a name. I'm going to call it n shock at time t. All right? Okay, and now the question about the length of the window. So it turns out that if you look at the shock centered around this n shock of t, the particles which feel shock are within distance t to the 2/3 over beta of this n shock particle. Okay, so the window is about order t to the 2/3 divided by beta. Okay, and the particles, they're fluctuating, of course. So x at t of n shock is here, but it has some fluctuations, and these fluctuations are of order t to the 1/3. Okay, so these are the kind of exponents that you also observe in random matrix theory. So there will be some random matrix laws that. Is that clear? Okay. All right. So if you want to study this process, you now index particles by time and space. So you take n shock and you look at particles whose numbers are within t to the 2/3 of n shock. So let's call that ntx, like so. And so x is the distance measured on scales of t to the 2/3, and there is the beta here. And then you look at the shock process, the macroscopic shock process, which is this psi of beta t as a function of x. Okay, so what you do is you look at the position of this particle ntx at time t, you subtract off its macroscopic position, and you divide by t to the 1/3, which is its the scale on which it fluctuates. And you would like to understand what happens to this psi beta t as t goes to infinity and then beta goes to infinity as a process of x. So here's a theorem, which is the following. So it says a couple of things. Okay, the first thing it says is that if you take the process psi and you take the large time limit, there is a limit. There is a limit in distribution, which is now a process indexed by beta and x. And then if you take that process and you take a large beta limit, there is a further limit, which is now just a process of x. And that, and in that sense, the process phi beta t converges as a process to this limiting function phi of x, which is maximum of 2 lines in x. So maximum of 2 lines in x. Okay. So the first line is minus x. And then it gets perturbed randomly by a GOE Tracy-Widom law, which is rescaled by this 2 to the minus 2/3. And the other line is also just the line plus x, and it gets perturbed by an independent version of this GOE Tracy-Widom law. Okay? So the GOE Tracy-Widom law, if you don't know, it's the scaling limit of the largest eigenvalue of real symmetric matrices. Okay? So it's also the scaling limit of top eigenvalue of real symmetric matrices. Okay, so it's the max of 2 lines which are height shifted by this, independent GOEs. So that's the theorem, and it doesn't sort of make sense, so I have to try to explain to you what it means. Are there any questions? Everything is clear? Okay. Okay, this is what it means, okay? So, well, if you look at the max of these two things, okay, as a process in x, you can represent it as the absolute value of x minus a difference plus a sum, where the difference is the difference of those GOE Tracy-Widoms, and the sum is the sum of those two guys. Okay? Okay, so that means the shock, the macroscopic shock process is converging to a V. Okay, it converges to a V. And this V, it gets shifted randomly. It is centered at this random D, and it gets height shifted by this random S. Okay? So it's just V, and it gets shifted in space and height. I should also say that there is a corollary of this, which is that if you look at the particle at the macroscopic position of the shock, its scaling limit is the max of 2 independent GOEs, which you just get by plugging in x equals 0 in this. Okay, so that's the corollary. You will see why I mentioned this. But the interpretation is that it is really the shock process is converging to this random V, which is centered and shifted. And now what does that mean? So if you recall, I wanted to say something about this tiny green curve, which is the particle density, the macroscopic particle density. Well, what is that going to be? That's going to be the derivative of the V. Okay, why is that the derivative of the V? Because the V is the limit of the particle positions. And the particle density is the integral of the particle positions. So if you want to sort of understand, in some sense, if you want to understand the limit of this tiny particle, the green density here, in this limit, after you have gotten to the level of the shock process, it's the derivative of the V, which is just an increasing step, which jumps randomly at this D. Okay. What does that mean? It means, first of all, that the shock in the TASEP is very rigid. Okay, so it's very rigid in the following sense. So if you start with the shock, okay, macroscopically the shock is always there. If you solve the Burger's equation, it's always this shock. It just moves in time. All right. Macroscopically, you may imagine that if you zoom in, you'll see some kind of randomness, some kind of very clever randomness. But there is no clever randomness. It is, in fact, still just a step function. And the only way randomness affects it is in the location where it jumps, which is this D. Okay? Otherwise, it stays very rigid. It remains a step function, even macroscopically. All right? So that's sort of the interpretation of the shock. Yeah. All right? Okay. Okay. So the reason I mentioned the corollary is this soft shock, which is what I call it, so I did this rescaling of these parameters, which I said was very mysterious. So this was discussed. It was introduced actually in a paper of Patrick Ferrari and Peter Neger, because we wanted to understand the macroscopic shock through this kind of limit transition. And they did some very nice simulations, and they found that, they conjectured what I call the corollary. If they found that at the shock, at the macroscopic position of the shock, you really have this product max of 2 GOEs, max of 2 Tracy-Widom GOEs. And so this is the proof of that. And the second thing is that there is something called the second-class particle in TASEP. And oftentimes people take the position of the second-class particle as the location of the shock, just by definition. So if you start with this kind of density in the TASEP, and you put a second-class particle at the origin, okay, then you can ask, does it really follow the shock? Okay, so is it the case that in the limit, in the scaling limit, it sort of moves at scales of t to the 1/3, and if you rescale, it's going to converge to the difference of 2 independent GOE Tracy-Widoms. And the answer is, in fact, yes, which was also proved sort of recently by this group of authors, Ferrari, Ghoshal, and Nejar, who showed that, in fact, this D is also the limit of the second-class particle. So in that sense, it is actually following the shock. Not for deterministic initial data. So that's the content of the next slide. So I say that at the very beginning that when you're modeling these densities, you have to use deterministic initial data, right? You can ask what happens, if you actually model the density by random initial data. So you put particles to the left at some probability rho, with probability rho minus, the integers to the left of 0 have a particle, probability rho plus integers to the right of 0 have a particle. In this case, you still have a shock macroscopically, but the shock fluctuations are not anymore t to the 1/3; they become of order t to the 1/2. And the reason for that is because this initial data that is random, it fluctuates on scales of t to the 1/2, and that overtakes this t to the 1/3 fluctuation of actual TASEP, which is the dynamical fluctuation of TASEP. And so, and in that case, the shock fluctuations actually become Gaussian as opposed to Tracy-Widom. So the thing that you were thinking about was probably the difference of 2 Gaussians as opposed to the difference of 2 Tracy-Widoms. No, so when you initially assign the particles at time 0, you have to do it deterministically. Yes, exactly. Yes, 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 anything, as long as it's done deterministically, right? Right. Okay. So the fact that you have this kind of T⁻² fluctuations of the shock when you have random initial data, this is a very classical series of works from the 1980s and 90s that's due to Pablo Ferrari and many other names, Kipnis, Liggett, and so on and so on. So this is very classical. Doing it for deterministic initial data is more difficult. Well, it turns out to be more difficult. Okay, let's see. So I mentioned this kind of auxiliary result, which is, what happens if you take this macroscopic shock process, psi beta t, and you keep beta fixed and you take a large time limit. I say, there is a limit here, which is very crucial to understanding what happens for large beta. So here's a theorem, which is that if you were to take this limit as time goes to infinity, so this will converge to some random process psi, beta of x, which can be expressed in terms of a random function, height function h, okay, so which I call h beta of 1. So this is a function of the variable x here. That's just the way it's rescaled. And this height function h beta is precisely what appears when you look at fluctuations of growth interfaces in KPZ models. So, so more precisely, it is what you would get. Don't have eraser. Oh, right. More precisely what you'd get. Okay, this is for people who may know this stuff, which is if you were to imagine starting your, imagine you have a height function h, which starts with like so. So you have a line, you have a v, whose slope is 2 beta here and minus 2 beta here. So the function here is 2 beta absolute value of x, okay? So if you look at KPZ growth, we started from this kind of initial interface. The growth at some positive time is going to be described by this kind of functions h beta. They're the same thing. And the point here is that these are sort of manifestations of the integrability of TASEP, namely that these correlation functions are determinantal. And to be more precise, what you'll get are formulas for the distribution functions of this h. So if you look at the probability that h, so this is the 1-point formula. If you look at the probability that h at a point x is less than or equal to a, it's given by the Fredholm determinant of some explicit trace class operator that involves heat kernels and some explicit operator k beta. And more generally, if you look at the joint distributions of h at various times, at various locations, you will get a more complicated looking Fredholm determinant that it also involves heat kernels, projections. So this chi is a projection, and also this sort of mysterious object k beta. So at heart of all of these formulas is this operator k beta. So okay, so these are all sort of Fredholm determinants of these of things, simple looking these heat kernels and something involving this new object k beta. And this, well, I want to give you a description of the k beta since this is something a workshop on. I forget the title of the workshop, but it has integrability in the title, so I have to mention this. So the operator k beta is the following. So first of all, you introduce a family of operators acting on L2. So you fix the number a here. So they act on L2 of an infinite interval, but it's cut off to the left. Okay? So not on L2 of R. And these operators explicitly are given by the exponential of 1/3 derivative cube plus x derivative square. Okay, so it's simple in that form, but they also have integral kernels, which is given in terms of Airy functions and just multiplied by some exponential. And now, if you want to construct this k beta, you have to follow our recipe, which goes like the following. So you will take a Brownian motion, standard Brownian motion, and now then you have to define a hitting time. which is going to be the following. So you look at the first time, a standard Brownian motion is going to hit, or is going to lie below this curve, which is 2 beta t minus u, where u is a parameter. Okay? So if you want, you can say I am starting a Brownian motion at u, and I'm going to run it in. So this is t. I'm going to run it, and I'm going to stop at the first time it hits this curve. Okay? Having done so, you're going to define a operator S hypo, which is an expectation of this S, okay, where the parameters that you choose are minus tau, where tau is this hitting time. The value of so the location where it hits, where the Brownian motion hits the curve, and then U and V have to do with this sort of. So S hypo is defined in terms of its kernel, and the U and V are the U and V in the kernel. So given this U and V, you start the Brownian motion at U, you compute this hitting time, you go in there, you plug in here minus tau u, the location where it hits, and then v, and also if tau is infinite, then you don't care. You want tau to be finite. Okay? So this is a recipe for computing this operator S hypo, and having computed this, K beta is just some combination of this S hypos and this S naught. See, S naught is just convolution against the Airy function. So it's just convolution against Airy function. And S hypo and their sums and products. Is that clear? Okay. So where is this K beta coming from? Well, I mentioned already, but this. I mentioned, so this object, this is defined sort of in generality. It was done 2 years ago in a paper of Kostel and Remenick, and I was going to explain this in some more detail, but then I saw that Daniel will be here next week, and he will probably explain this in a lot of detail, so I will skip those details. But what I will say is that there is a description of this S hypo as an explicit limit of a product of 3 matrices, a product of three operators, one of which is the Airy kernel, which is a very explicit object. There, you can write down its matrix. Then there's the heat kernel at negative time, minus L. So L is very large, and you're looking at the heat kernel at negative time. That looks very bad, because heat kernels don't act very nicely on L2. They act nicely on nicer functions. But the point is that it acts very nicely on the Airy kernel, because the Airy kernel is projection to the negative eigenspace of the Airy Hamiltonian, and those eigenvectors are very well behaved when you want to apply the heat operator at negative time. So it's very nice behaved. And then there's this critical object, which is some kind of hitting density, P hit, which is nothing more than the probability density. So if you look at its kernel, it's nothing more than the probability density that a Brownian bridge from U at time 0 to V at time L hits the hypograph of this curve. So what you do is you fix U and V. This is L, this is 0, U, and so maybe V is up here, or maybe V is down here. And what you want to do is compute the transition density of a Brownian bridge to go from, say, here to here, while hitting the hypograph. So hypograph is everything that lies below the graph. You want it to go from here to here, while hitting here, or maybe you want to go from here to here, if V is down here, while hitting the hypograph. Well, V were below the hypograph, there is nothing to compute. But if V is above the hypograph, then you have to compute something. And if you can compute that, then you can get this explicit expression. And by taking its limit, you can actually compute this S hypo. And computing this S hypo is crucial if you want to understand this problem of the shock, because you have to be able to compute K beta. It's not just enough to be able to write a recipe for it. Okay? So this kind of interpretation as a heating operator is very crucial. Functions which are lower semi-continuous and grow at most linearly. Right? So these kind of things are. Okay. So I want to make a few more remarks. So this H beta, I already say that this is what it does is it looks at KPZ growth interfaces when you start with this kind of wedges of slope 2 beta. So to make that more precise, let me say that you can take various limit transitions of this H beta in beta to get all the Airy processes. So if you take beta going to negative infinity, it will give you the Airy2 process minus a parabola. Okay, so that's, that has to do with the fact that as beta goes to infinity, this curve, it becomes what is called a narrow wedge, which is what was mentioned today in the morning. If beta is 0, then you get the Airy1 process, which describes growth interface from a flat piece right here. And you can also get the Airy2 to 1 process by doing some other kind of limit transition. So this Airy2 to 1 process it describes sort of KPZ fluctuations when you transition from curved data to flat data. Okay, so you can get all this kind of things. For those of you who are interested in random matrix theory, you probably know that random matrix theory now has 2 parts. One part comes from physics and has to do with Wigner law and so forth. The other part comes from statistics, and it has to do with something called Baik-Benaru-Pesce transition or phenomena. It's really about 50-50 now. Maybe in 10 years it will be like 70-30. But this kind of soft shock scaling is an analog of this kind of Baik-Benaru-Pesce scaling that you observe in random matrices, but within this context of particle systems. And this kind of height interfaces are sort of the corresponding limits so in the random matrix world, you would take a Wishart matrix, add some rank 1 perturbation, and look at the largest eigenvalue. Here, you sort of look at this kind of height, this kind of particle positions at the shock, and if you were to describe them in terms of this height function, that would be the corresponding thing in the world of particle systems. So these are all if you think of this soft shock, what it is doing is it's taking a flat initial data. Just to be very precise about what I mean here, if you look at soft shock, what you're doing is you're taking a flat initial data and doing a very tiny perturbation. Okay? And you're understanding sort of what is happening here in this regime where you do the perturbation. And in that sense, it's sort of very similar to this kind of Baik-Benaru type thing. All right? Any questions? Okay. So I want to mention a few things about the proof because I gave all these formulas. So I want to explain how they work. So suppose I want to prove, suppose I want to understand the distribution of H beta at the spatial point x equals 0. Okay, so this is a, so we want to compute, to take the limit as beta goes to infinity. So if I want to compute the probability that psi beta 0 is less than or equal to A, I have to compute this probability, which I know is given by this Fredholm determinant. Okay? So now I translate to put the beta in the operator, so I'm going to get a Fredholm determinant over L2 of this operator, where this is just a translation. Yeah, I just did a translation. And now you have to do 2 things. You have to compute k beta, and to be able to do that, you need to compute the hypo. Okay? And then you have to somehow show that in the limit, this is going to converge to a square of a F1 distribution. Okay, so how are you going to get a square of a distribution? Okay, so you have a matrix, and you want to somehow say its determinant squares. Well, there are basically 2 ways that you can have the determinant of A being the determinant of B times the determinant of C. One is that A looks like the following. So if you think of A as a matrix, it will look like the following. It'll have a block form where you have a B here, C here, 0 here, and whatever here. If you have something like that, then it's definitely true that the determinant factorizes. And the other way it can happen is that A is simply B times C. Okay, so here also you have product of determinants. And it's the second way that appears here. You have to factorize this this object. You have to factorize it. And this is actually a very crucial technical point. It took about 2 months to figure out this factorization. But once you figure it out, it takes about 2 minutes to check that it is correct. So this is somehow a crucial point that you can sort of factorize this kernel once you can compute k beta. Okay? So I have about 5 or 10 minutes or so. So I wanted to say a little bit about how you go about doing that. So what happens is, so this S hypo, I told you have to calculate it. So here's the lemma that tells you exactly what it is. So you have two basic operators. One is multiplication. So you multiply by e to the beta x. This is one operator. And then you have the reflection, which given a function just reflects it. And S hypo, well, it's a sum of two things. So this chi naught is cut off below 0. Okay, so chi naught is 1 if it's chi naught is projection to L to negative infinity 0. Okay, so in S hypo, if you were to start from below 0, there is nothing to hit. Okay, so that corresponds to the fact that you have this S naught times chi naught as one part of this thing. And the second part is what happens when you start from above 0. And when you do so, you will see that you get something which is the conjugation of the reflection operator multiplied by S naught. And remember, S naught was convolution against the Airy kernel. Not the Airy kernel, but rather Airy function. So you have convolution against Airy function, and it gets conjugated by this kind of reflection. Okay, so that's what S hypo is. And then when you write down identity minus this k beta with the translations, you will see that it has a factorization of this form, identity minus q transpose times I minus q, where q is a conjugation of an operator A and something else which is a mistake, which is going to go away in a large beta limit. Okay? And A is the operator which is associated to the GOE Tracy-Widom law. So if you take the determinant of 1 minus A on L2A infinity, that gives you the distribution function of the GOE Tracy-Widom law. So that's how it comes. Okay? So imagine you take determinants here and you get a square of the determinant of I minus Q. Well, because there's a conjugation, you can remove that. Okay? So it doesn't matter. And this E of beta is an error that's going to go away in some trace norm as beta goes to infinity. And so in the limit, you will get the determinant of 1 minus A square, which is how you get the F1 square law. All right? So that's so I just explained all of this. Okay? So that's how you get the factorization. The hard part is here coming up with this factorization. I wanted to mention how to calculate the S hypo, but since I'm almost running out of time, I'll say that well, I will skip this part. And I will go to the end. So you can calculate S hypo using reflection principle, because you have to calculate the transition density of Brownian bridges, and you have to sort of calculate it with respect to a line, and you can always turn that into a flat line and use reflection principle to actually calculate that probability. Okay? So you do some reflection principle to do that. So that's the part I will skip. And now, to finish, let me just say that, so this had to do with what you were asking. So I started with something which was already at a shock, okay? But now I can ask, okay, what happens, if I start with the initial density which has multiple jumps, so 3 jumps or 4 jumps or 5 jumps, okay? So if you were to model this kind of densities and run the TASEP, in finite time, they would sort of merge into one step function. And you can ask, what's going to happen? What are the fluctuations just as it merges into one step function? And a very similar approach will tell you that at the level of the process, it's given by a maximum of lines, where the number of lines is equal to the number of jumps, or maybe one more than the number of jumps. And all of these lines are perturbed by random independent GOE Tracy-Widoms. And now you can ask, which is the very interesting question, what happens when you start that? So this is a continuous data. There is no shock. Okay? If you run the TASEP, it will run into a shock in finite macroscopic time. And you can ask what happens. So you can imagine this as being sort of a collection of many small steps, right? But that doesn't necessarily mean that it's going to be a limit of this, all right? Because the order of the limits are very different. And this is a rather interesting question. there is a chance that here what you will get is a new distribution, which tells you, the distribution of things which you observe when you run into a shock from continuous initial data, which was sort of the problem I had started with at the very beginning. So I'm out of time, I think, so I will stop.
Other questions? If not, let's thank the speaker again.